size is probably why it was getting cut off.
I don't do that. We still don't get everything. Okay. So I'm going to talk about direct n-body calculations. It's a pretty simple algorithm. I'm sure all of you know exactly what it is, but I wanted to talk about it for a minute. And which one? Number 2? Number 1. So in the, this is it showing up very well? And what else do you like to do, Mark?
Hit the twiddle key to hide the slide. Maybe not. Don't worry about it.
Okay. Maybe. So this is kind of nice because one thing that surprised both Mark and I is that it's running faster than we've ever seen it. And we wrote the application. It's on an overclock. Did you say it was overclocked? It's a 8800 GTX Ultra made by Alienware and everything. You know, turn all the knobs up. And so it's running faster than we've ever seen it. It crashes a lot.
Made by Alienware, crashes a lot.
All right. So this is an example of getting 265 gigaflops on one of our machines. There are 16,384 particles being simulated, and gravity is the force that's being applied. There is Mark has a damping.
What's the algorithm?
What's the what?
The algorithm?
I'll show you. It's just the dumbest, simplest one you could think of. But so you put a little bit of velocity damping, and everything gets oily. You know, it gets thick, and they'll all collide. It's very goopy. Anyway, there are a bunch of parameters you can play with. This is on all the machines. You can play with it tomorrow. You can play with it when you get home. It's compelling. We like it. Okay, so you guys just want to sit here and watch it for the rest of the day? Okay.
All of the machines upstairs in the library, so
you can just go up there and just all night. Yeah, you can change it. All right, so we wrote this just sort of to see where the G80 was. The G80 came out about a year ago. Mark and I talked about. Did we talk about it this time? We just did it. You did it and I did it?
Yeah,
I don't remember. We both did it and realized that we both did it and joined our codes together. And we both found interesting bugs in the compiler that the other one didn't find. Anyway, we wanted to see how n-body methods would run on the G80 using CUDA. And I'm Lars Nyland. I'm in the compute architecture group at NVIDIA. I don't usually get to see people like you, customers. I am heads down. I'm working on, what you're going to use sometime after today. Sometime in the future. And when I'm done, Mark takes over, or maybe 6 months go by and then Mark takes over and starts showing developers how to make use of all the stuff that we've done. More? Better? Faster? Okay, and then we also did this work with Jan Prins, who's the chair of computer science at University of North Carolina, and he's interested in using it as sort of the building block for either fast multipole methods or tree methods or some other hierarchical code. Okay. The target machine, as you well know, is the G80, 128 processors, 1.35 gigahertz. Multiply those together, you get 172 gigaflops. If you count MADS as 2 operations, you get 345 gigaflops, which the CUN body guy was saying, that I think that's where he got his number, 345. But his code runs at 380 gigaflops, so somehow I don't know. Anyway. With some magic, you can get up near 500 gigaflops. There are 16 multiprocessors, as Dave told us today. And we really think of running 32 threads at a time. Even though we show these pictures with 8 little processors, forget the 8. We run 32 at a time. And it takes 4 beats of the clock. And then one thing I like to stress, people think when Dave or Mark say data parallel, they mean SIMD. And I want to get away from that. This machine has 24 program counters on each of the 16 multiprocessors, so it's got 384 program counters. They don't have to be in the same place. They can be all over the place in your single program. And they can race ahead of each other. The 32 threads that are doing this part of the loop, may get stalled on a load. And some other warp, which is what we call 32 threads, may run way ahead. They're not tightly bound. So anyway, I'm just saying all this stuff. We don't have to pay a SIMD penalty where we have to execute both halves of every if statement. If a bunch of warps, a bunch of threads in a warp 32 at a time go one way through an if statement, you never have to come back and do the other way. If they alternate, you're going to have to do both sides. But so it takes a little bit of thought to get this to act like more than a SIMD machine. Okay.
Can you say more about the target problem? This is the target machine. I missed, maybe it was the previous slide.
I just was talking about, it's really simple. I just wanted to write an all pairs direct n-body app and see how it ran.
I understood that, but why? Can you say that?
Because it's sort of the lead in to everything else in n-body work. If you get an idea of how well that works, you can go on and do PME and couple that with direct, or you can, I used to work in molecular dynamics, some with John a long time ago, but more in North Carolina. And the direct method is always a fundamental component of all the work I've ever done. And so, you want to couple that with a fast multipole method. You still have to be able to do the direct calculation very well. And so that's sort of, it's the fundamental part.
And I wanted to do it so I could see how many gigaflops I could get.
Yeah, we just want to see gigaflops, right? My boss is an architect. He wants to know gigaflops. What's something close to a real app instead of a totally synthetic instruction stream? Okay. It's pretty easy. Compute all the forces between all the pairs, sum, and integrate. The nice thing about the direct method is its accuracy. Maybe not. Some people were arguing earlier today that the accuracy dwindles as you get n growing. And it's reasonably slow. So here's the big equation, right? You learned this in physics in college. And so I'm going to go through these quickly.
Where's the negative sign?
Yeah. Oh, I forgot. It's electrostatics. I wanted to add the vector over here, the unit vector. This is something that the G80 does very well, is vector normalization. Commonly, we soften the distance with an epsilon. This has some theoretical benefits, and it certainly has a computational benefit that there's no divide by zero. So I don't have to have an if statement anymore. Right? I can throw that if statement out. We really want the acceleration, not the force. We get the total acceleration by summing all the individual accelerations. And this is sort of and this is what I use, or what we used. And like I said, division by zero is not a problem. And when I count this out, I get 20 floating point operations. In the literature, who was talking about? The chamomile, 38 is a commonly cited number from Warren and Salmon at Caltech. I don't know where they got 38, unless they said square root and divide are just 10 each.
I've seen people do things like that in papers where they count them as well.
I don't know why it's 38. We say 20. The guys from Stanford call it 19 because they think 1 over square root of x is one floating point op.
I think you're going to have to put Martino in English because he did it like that when he was making the...
Okay. Well, in any case, the 38, the 38 is a common number, but when I count, I get 20. And I don't count, this add gets counted the same as a square root. Is that fair? It's just bad hardware designers who can't make a square root as fast as an add, right? Get on it.
The definition of floating point operations becomes a bit vague when you start talking about zones.
Well, you're right. So this has, as long as you're happily living in matrix world, right? We have multiplies and adds going on. It's easy. But when you throw in a divide or a square root or a 1 over square root of x, is that 1? Is that 2? Is it 20?
The difference between all the different numbers, I think, is only because of the matter of space.
Right. And so this is the reason I want to show you this equation, because I want to talk about how many of these evaluations I can do per second. Let's not get bogged down in how many actual flops there are. Let's talk about fractions per second, not gigaflops. What?
The science rate, not the...
Yeah.
Well, and another reason, can I say, another reason for that for us is that we know theoretically how many of those per second our hardware can do peak. And so by measuring how many we actually do, then we can get an idea of efficiency on our hardware.
And for some of the difference between 19 and 30 or 38 is insignificant.
Okay.
We're done for this.
It's always in the same order of magnitude. If you have higher
All right.
about 10, then you're fine.
So when I think about this method, I always think of a big square. At each one of these green squares, I want to calculate the acceleration between particle I and particle J, and it's cutting stuff up. But so the most parallel you could get, you could even go beyond this. You could do every one of these boxes as a separate thread. Seems like way too much overhead. So we'll talk. I think it's right now. How many threads should we use for this? On the one hand, you want to have enough to keep the machine busy. Mark talked about this. We have 128 processors. They need to have about 24 threads each to hide all the latency in the pipeline. So I get 3,000 threads is a good number to start with. And you'll see in some of the performance numbers that I have, when I go down under 3,000, you'll see some dropping in performance. And it's all because we're not keeping there are empty slots in the processor's cycles, and we can't fill them up. That doesn't mean you can't go below that number and still get great performance. When I drop down to 1,000 threads, I still get way better performance than a serial CPU. So it's not that big a deal to drop below it. I wanted to get equal distribution. We have 16 multiprocessors, so I want some multiple of 16 typically. I don't want to have 17 because 16 will run all together, and then one will just be lonely. And it'll cost as much as doing 32. So I want some multiple of 16 blocks. And then we don't want too many because, as Mark was just talking about, first there's going to be overhead of the parallel computing. You're going to have to do some computing. You might have, some communication, some synchronization. And if you have all this stuff all spread out, then you'll have to do these log n reductions. And if you've got enough parallelism without that, it's going to do one row. Each thread is going to do one row of that big grid I showed. And so it's going to be sequential. It's just going to go along. And each thread is just going to cruise along in that big grid. And we're going to write the total acceleration out to global memory. Then we're going to wait for all the threads to finish, and they all write their accelerations. Then we're going to do this integration phase where we pull all those accelerations back in, update the positions and velocities, and finish all those. There's a synchronization that's implicit between these, what did you call them, thread blocks, thread launches, kernel calls, the things with the 3 angle brackets. Yeah?
Just remember something about the 38. The 38 also includes the potential calculation.
Okay, so I was just reminded that the 38 flops in an interaction also have to do with calculating potential. Okay. So here's just a picture of what I just said. We have one thread that's going to run all the way across this big grid. And as Dave and Mark pointed out, you need to make use of this shared memory. It's very fast. It's very close to the processing unit. And global memory, if I had a bigger screen, it would be, out on US 1. It is out there. And so you want to make sure, if you're going to use any piece of data twice, the second time better come out of here. And so, like Mark was saying, the typical thing on the G80 is to take these blocks that fit in shared memory, haul it all in, do all the calculation on as much data on the data that's in here, and then go get another block. This makes it much, much more efficient. The blocks get mapped to different multiprocessors, and I just basically break this into some number of blocks. There's no communication across the blocks, so you can just all run across and sum their accelerations across. And then we want to break these long rows into these tiles of computation. And I'm going to just go to the next slide, which has a picture. I fetch my own position into this array here, and then I go and fetch the same number of some other positions, and I'm going to call this dimension p across and down. I'm going to do p squared interactions, and then I'm going to synchronize with these red lines. Then I'm going to haul in the next set of other bodies to work with into the shared memory, do the p squared interactions, and go on. And so I have this fetch p-body data, do all the p-squared interactions, synchronize. Fetch again, do all the p-squared interactions, and just go on. And this is how it proceeds. And you really need two synchronizations, because things can get really out of skew here. If this is on the machine that you were watching, is this 128 by 128, 256? It's 128 by 128, and so there are multiple warps in it, and the warps can get ahead of each other across these grids, 32 at a time. And so you don't want the 32 up here that finish, go ahead and load some of this data while these guys are still coming up. So you need two different synchronization points in this loop, not just one. Because you don't know how the warps are all going to, when they're going to get here. This is tricky. It took us a bit of arguing in our head about what that's going to do. What you get by using the shared memory and reusing data, if you don't do that, you have to read n squared positions for every step. When you tile it, you only read n squared over p. And so you save, the bandwidth to memory is divided by one of these nice, they're not horribly large numbers, but they sure do reduce the memory bandwidth. So that this whole application, the memory system is just not doing much most of the time. We're down in the units of gigabytes per second, 1, 2, 3, 4, well, where the machine can sustain 60 or 80 gigabytes a second. So we're not using the memory bandwidth at all when this is going on.
It's the difference between order n squared bandwidth and order n.
Is it?
Well, I mean,
okay.
it's not order n squared.
The initial results we got were 8.5 billion interactions per second. And like I said, I'm counting it at 20, so it's just 170. And so we tried some optimizations. Loop unrolling is a fairly common thing to do. Get the loop overhead amortized over several loop bodies. Changing the block size, seeing how that affected it. And then when n gets small, you get into these inefficiencies where there are not enough threads, and so you need to get more threads into the work load. And so when n gets small, we tried adding more threads and had some good success. Loop unrolling is about as primitive as it gets. I had this, I changed it to this. Copy, paste, paste, paste. And fix up the updating of the loop index. This is one place where, well, I don't know. Sometimes this uses more registers, sometimes it doesn't. I don't know what it does now. It shouldn't use any more registers, but it did for me, but it didn't for Mark. You have to experiment, and we could never.
It's one of those things I still don't trust in the compiler.
Right.
It's still faster to unroll.
Yeah, it's still faster to unroll, and here's the example of unrolling. There's 3 different problem sizes. There's 1,000 bodies, 4,000 bodies, and 16,000, and these are the gigaflop numbers. So you can see, like on the 4,000, we went from 163 to 181. Get rid of some of that loop overhead. I looked at block size. This is how big the tiles are or how big the block is. And I started artificially low. I started at 16. So I don't have 32 threads, and it wants to run 32 threads together. So I'm only getting half the machine utilization. And you can see it goes up significantly, at least for these two, by actually filling up a warp. And then the other thing I wanted to show is that bigger is better until you have too few blocks. Since a block goes onto one of the multiprocessors, you need to have enough blocks for all the multiprocessors, or else you're going to they're going to go idle, and that's what's happening right here in this downward section, because this is only 1,000 bodies. And so you start dividing 1,000 by 128 and is 8, so half the multiprocessors are idle at that point. Okay. And then the last optimization we worked on was when the row is too short, we break it into either 2 or 4 sections and put 2 or 4 threads on each row, and then just the first thread collects the data. We don't do any log n. It's only 3 things it has to pick up. It's not worth writing tree codes. Get, and go. And so the effect of that, these are different problem sizes, 1,000 bodies up to 3,000 bodies. And I went from 1 thread to 2 threads to 4 threads. And we got nice speed up. We went from a little over 60 gigaflops to over 100 gigaflops. So this helped out a lot by getting enough threads to keep the machine busy. Above 4,000, it made no difference at all. We had enough work. It's just stuff getting in the way. So, there seems to be this magic number around 3,000. that keeps the machine busy. Okay. And then this is just overall performance, compare, the size of the problem versus the gigaflops that we're getting. Although, as you saw in the demo, that this number should now be up at, 265? Yeah. Yeah, so it's gone up quite a bit from what we had last January or February. So the direct method, because of the reuse of the data, just maps so well to the G80 hardware with this little shared memory that is register speed. You can do all these p-squared operations for just fetching p data, and it just fits so well. We get nice high performance. Depending on who you ask, what their CPU code runs at, I think we're getting about 250 times. And there's two reasons. One of the most important ones is this: we have 1 over square root of x is a single instruction, takes 4 clocks, or I don't know how you count clocks these days, but it takes a little bit more work than an add. Whereas on a Pentium or Intel processor, a single precision divide takes 23, and a single precision square root takes 23 clocks, and they're unpipelined. Some people turn to the SSE inverse square root instruction, but be warned, it's 12-bit accurate.
Yeah, it's actually an estimate instruction. It's not really.
Right, it's an estimate and inverse square root.
You have to then do Newton-Raphson a couple of times to get it accurate. Right,
but that takes that's like 18 clock cycles or something, right?
I think that if you just use square root in our math library in CUDA, it uses the estimate and then iterates also.
You think so? I don't. No, it doesn't. I've looked at the code.
Oh, does it?
R square root.
Yeah,
Bam.
They do something else. I think Massimiliano posted the algorithm they used for that.
Okay.
And then the last thing I wanted to end with is that the shared memory is not a cache in the traditional sense. There's no tagging hardware. There's no sets. There's no ways. It's not a cache like you're used to on a Pentium or a MIPS or whatever else. It's just a cache in the oldest sense of the word. It's a secret little place where you can store stuff, right? You get to choose where it goes, but on the flip side, you have to choose where it goes. So, it's double-edged. You know exactly how it's going to perform, but you always have to say how it's going to perform. Yes?
It's not better to just call it a scratch pad?
Sure, it's a scratch pad.
Yeah, the PTX, not PTX, the parallel thread cache name was a marketing decision. Oh, the parallel data cache, yeah.
Yeah, I don't call it a cache. I call it shared memory. I call it shared memory or a globally addressable register file. Right, where instead of saying R7 for a register, you say R of some address register. It's just a register file.
It works like a regular file, right?
Yes, it is a register file. And it's just that all threads in a block can access any location in that register file. It's very fast. Okay, and we already saw the late breaking news. We're getting better performance with these improved drivers. We had 210 on our machines, and Mark hit 240 a couple weeks ago.
How the driver affects the performance?
The compiler tool, the compilation tool chain basically has improved.
There's software always has bugs, right? We fixed some bugs. Okay, and I think that's it. Any questions?
So, have you compared this thing to any optimized algorithm? I mean, algorithmically optimized n-body simulations like...
No, I haven't compared it.
Because this gets big performance, but I mean, if at the end of the day you have...
So the question is, have I compared it to any known quality algorithms? And the answer is no. I'm an architect, and I had to steal time from my boss to get this done. I work on other things most of the time.
For some of us, this is
I know.
we want direct n-body. Yes.
Yeah.
No, but if it's slower than if you do FMF...
We want direct
No, they want the accuracy. And somebody else?
I was just going to ask, I've seen this two different ways. The number of threads in a block, maximum. 512, 768.
It's 512.
512.
Well, yeah.
From CUDA, you can only get 512. The machine can hold 768, and so what you can do, which is what Wenmei Hu's class figured out, was you can run 3 blocks of 256, and they'll all fit.
Yep.
How'd they figure it out? We know it, but they figured it out on their own, right? So all the applications, there's a paper. You do teach it? Okay.
I think all we did was we read your documentation. There's no magic. I played with that with the occupancy calculator.
So can I try to give an authoritative answer?
Yeah, do it.
The authoritative answer to why is it sometimes 768 threads and why is it 512 threads sometimes is that the hardware was built to handle 768 threads. The CUDA software team set the limit at 512 threads per individual thread block because it was found in their tests that was almost always, going above that was almost always a lose. The more threads, the fewer registers per thread. And so 768 was forced to squeeze down to like 5 registers per thread or something, and only the most trivial synthetic benchmarks would fit in that. So I think they made an executive decision to limit it to something reasonable so people wouldn't end up in this sort of place in the design space that was very unlikely to be a win. But the machine does handle more, and in fact you can launch 768 threads if, as they said, if you launch 3 sets of 256 threads.
I find that I run out of other things first. I run out of shared memory, or I run out of registers. Yep. There are several resources that, if any one of them runs out, you're done allocating work to that.
It's even hard to get down to 10 registers. I can't even imagine somebody getting down to 5.
Not for anything useful.
Yeah.
Can I ask about the distance calculation? Did I understand that right? That you assume the on-device function to calculate distance?
There's reciprocal square root.
Yeah.
But you still have to get the squared distance yourself.
Okay. So
you still have to do the multiply, add, multiply, multiply, add, multiply, add.
And that is at the 23-bit accuracy of...
It's all the reciprocal square root is 20. It's 1 bit less than everything else. It's 20. I think it's 22 bits instead of 23.
Is that accuracy of all these on-device functions improved with the double precision involved?
Okay. To repeat the questions were about the accuracy of the reciprocal square root function, and I was about to make the general comment that the lib math, if you just type square root f, you get higher you get the same precision that C standard library gives you, whatever that is. The underscore square root f intrinsic, which accesses the hardware accelerated version, is lower precision. Lars thinks 23 bits, as you heard, and considerably faster. And so, as your question, will that change? Will these custom hardware intrinsic? Will the precision of these custom hardware intrinsics change with double precision? The short policy answer is we're not talking about the double precision hardware in that specifically yet. And the longer answer is I have no idea. The even shorter answer is I have no idea. Like what's happening with that particular aspect of double precision support. Like that's a weird device. In general, that stuff exists. Is it fair to say that just I don't know what they're doing, but the policy in general that those custom hardware intrinsics exist because they're extremely useful for graphics. You use them all the time. Yeah,
the inverse square root is. I mean, you think about lighting, right? You want to do reflections off surfaces, right? You need a unit vector, and
you need unit vectors all over.
You need unit vectors all over the place, and so you need 1 over square root of x.
And that's one of the reasons some of the codes that do things like those potential kernels run so fast on the GPU. Also, the same reason.
And there are all these beautiful hacks on serial code to get 1 over square root of x. If you look in any gaming forum and ask for inverse square root, they'll show, and you look at them and you're like, I can't believe that works. I can't even tell how that works. It's just like some constant, 7.77123 times this, a few more instructions, and it's just, wow.
It's all about getting good at it.
Yeah.
Yeah, my question is the architect of the GPU. So, is there any physical limitation or in future plans to make some cards with larger shape memory because when we did this, all this kind of lack of this is actually very important. I don't know.
The
so small. I mean.
Well, if you think about it, it's what is it? 16 kilobytes times 16, so it's 256 kilobytes on a chip of registers, and then that's half the size of the register file. So the register file is another 512 kilobytes. So we have 3/4 of a megabyte of register file on a chip. And you want? Would you like fewer processors? There's only so much room. Well, the answer is there's only so much room, and you wouldn't believe how long these discussions go on. 16K, 32, 48, 64, and so we watch the shrink rates at the chip fabrication. At TSMC, they've got 55, 45 nanometer. What are we going to do when they go to 45? We're going to make the shared memory bigger. We're going to throw more multiprocessors on. A little bit of both. How do you allocate it? And what the best thing to do is to have a compelling application and say this application would run, this much faster for this much more shared memory. And if you guys have an application like that and you send it to me, I'll put it into the test suite. And so when we're doing these sizings, it'll show up.
And if your application involves billions of dollars behind it,
yeah. If you have 10 million users and you're selling it for $100 a piece.
Do you have an emulator that you use to perform that kind of estimate?
We have simulators at all levels, and then I've heard that we have more emulators than anybody else, hardware emulators. We boot up the chip in these big boxes, and there's a PC with wires coming out of it, and we boot it up and run it in the big emulator.
I haven't seen it, but I've heard it's like an FPGA the size of a tractor connected to a PCI Express board.
Yeah, you have this PCI Express board that's running into this. It's a refrigerator on it. It's more than a refrigerator. It's like 4 refrigerators, and we have 3 of them. I think we have 3 of them, and they're always busy. I believe they're FPGAs. And we simulate. I don't know what it is. And it only simulates a small part of the chip. It doesn't do the full 16 processors.
You need to get your simulator running in CUDA.
We do. Why don't we run the simulators in CUDA? All right. That sounds like the end of a day. We're ready for posters.